In Strength of Building Material 2 of Lecture 1, we are going to be talking about the introduction to structural analysis. In our lecture outline, we have our intro, classification of structures, type of load on structures, support and equilibrium equations, principle of superposition, static determinacy and stability, numerical classification of structures, and some work examples also as well. In our introduction, a structure is a system of connected parts designed to carry load and provide adequate rigidity. The connected parts are called structural elements that are beams, columns, slabs, shear walls, and etc. etc. We say a structure is a system of connected parts designed to carry load and provide adequate rigidity. Thank you. In our structure analysis, we are saying structure analysis is the prediction of the performance of a given structure under prescribed load and or other external effects, such as support, movement, and temperature changes. The performance characteristics commonly of interest in the design of structures are stresses or stress resultants such as axial force, shear force, and design bending moment, deflection and support reaction. Thus, the analysis of a structure usually involves determination of these quantities as caused by a given loading condition. Okay. In our classification of structures, we are saying common structures are commonly used, or let's say commonly used structures can be classified into 5 basic categories depending on the type of primary stresses that may develop in their members under major design load. So we have tension structures, we have compression structures, we have the trusses, we have shear structures, and also the bending structures. Please take note. Note that any 2 or more of the basic structure types described above may be combined in a single structure. The selection of the type of structure to be used for an engineering project is the responsibility of the structural engineer. So it is not the responsibility of a building technologist to design a structure, okay? But we are only reading this course so that we will be able to understand the drawings provided by the structural engineer. Thank you. So this is an example of tension structures, okay? These are examples of tension structures. And these are also examples of, let me say, compression structures, okay? You can also see trusses. You can see how it looks like. Okay. So we are saying, let's talk about shear structures. Shear structures develop mainly in plane shear with relatively small bending stresses under the action of external load. Shear structures such as reinforced concrete shear walls are used in multi-story buildings to reduce lateral movement due to wind load and earthquake excitation. Okay, so this is an example of a shear structure. Okay, it is designed to be able to handle what? Wind Okay. So this is also an example of a bending structure. Okay. So all the structures we have seen above are all always subjected to loads. Okay. And the loads which they are being subjected to may be a dead load, a life load, impact load, wind load, snow load, earthquake load, hydrostatic and soil pressure load, thermal and other effects, and also load combination. The load that act on common civil engineering structures can be grouped according to the nature and source into three classes that are dead load, life load, and environmental load. And these environmental loads we are talking about are the wind, snow, and earthquake. Wind, snow, and earthquake. So the wind, snow, and earthquake are environmental load. Okay. The dead load itself are the components that are attached to the building itself that cannot or are not movable. Okay. An example of a dead load is, let me say, the roof on the building. It's a dead load. Okay. You can imagine the number of load that a building that is having a heat proof is carrying. It's not easy at all. Okay. And the life loads are the human beings and the movable objects. Okay. And these environmental loads we are talking about are the wind, snow, and earthquake load. Okay. So let's talk a brief about the thermal and other effects. Thermal load are due to temperature changes on structures. Statically indeterminate structures may be subjected to stresses due to temperature changes, shrinkage of material, fabrication error, and differential settlement for support, although these effects are usually not addressed in building codes. They may cause significant stresses in structures and should be considered in their design. Okay, so let's go on to talk about the support and equilibrium equations. Support and equilibrium equations. Good. So type of support for plane structures. Okay, you realize all the structures we saw initially are either having uh, a hinge support, a roller, or a fixed support. Okay, but before we dive deep into that, let's kindly take a note of these few aspects. Supports are used to attach structures to the ground or other bodies, thereby resisting their movement under the action of applied load. The type of reaction a support exerts on a structure depends on the type of supporting device used and the type of movement it prevents. Support for plane structures are commonly idealized as either fixed, fixed support, hinge support, or or link support. Let's talk about the fixed support. It said the fixed support do not allow any movement. Okay, an example of a fixed support is the pillar in, or let me say the column in our classrooms, you can see that it has been reinforced with a concrete, so it cannot allow any movement. Okay. When it comes to support, they prevent translation but permit rotation. We say the hinge support can prevent translation and permit rotation. But for roller or link support, they can prevent translation in only one direction. Okay. So let's kindly look at the type of support for plane structures. Okay. And this is our category. The first column is the category. The second column is the type of support. The third column is the symbolic representation. The fourth column is the reaction. And the fifth column is the number of unknowns. Good. Let's look at the roller, rocker, or link. Okay. So you realize that the roller support is having just a round ball. Okay. That is serving as the support. Okay. Take note. In questions, it may either be represented as this or this. Okay. This and this are all the same thing. Don't let this confuse you for something else. I'll come back to this later. And the reaction for the roller, this is how it look like. You can see that it has only what? It has only one reaction, okay, which is moving to the north side. Okay. Or it could also be represented as this. The reaction force R act perpendicular to the supporting surface and may be directed either into or away from the structure. The magnitude or the magnitude of R is the unknown. Okay. The magnitude of R is the unknown. Okay, we are saying the reaction force R acts perpendicular to the supporting surface and may be directed either into or away from the structure. The magnitude of R is the what? Unknown. Okay. So this is how the rocker supports also look like. Okay. This is how the rocker support also looks like. And this is the reaction. Okay. It also has the same number of unknowns as the roller support. Okay. And for the link support, you can see how it is also being represented. Okay. You can see how it is also being represented. They all have one reaction. Okay. The roller, the rocker, and the link support are all what having one reaction. The number of unknown for the link is the reaction force R act in the direction of the link and may be directed either into or away from the structure. The magnitude of R is the unknown. Good. Let's come to the hinge support. For the hinge support, you can see that it is this beam, this is a beam, okay? This over here you are seeing is a beam, okay? And this whole beam is being supported by this you are seeing over here, okay? This whole beam is being supported by this thing I just circled beam, okay? This whole beam is supported by this. It may either be represented as this or this. Okay. Please, you always have to know that they are the same. Okay. If they don't put it this way in questions, they'll put it this way. Okay. So please take note. I said I'll be coming back to something earlier, and that is you realize that this hinge support is similar to what the roller support, but bear in mind that they are never the okay. You can see that for the roller support, this thing over here, like a cap, is having two balls under it. Okay, but for the hinge support, it does not have any two balls under it. Okay, it's just like, let's say, a cone that is lying down. Okay, yes, just accept it from that perspective for me. It's just like a cone that is lying down. There is no balls under the cone. Okay, other than the roller support, it's like a cone that two balls have been placed under it. Okay, so that is how the whole picture is looking like. Let's come back to our hinge support. Our hinge support is having two reactions. Okay, our hinge support is having two reactions. You can see that the first one, which is the X, is moving to the hot east side. Okay, it's moving to the east direction. And the second one, which is the reaction Y or RY, is moving to the north direction. It's moving to the north direction. So what have we learned so far? We have learned that roller support, rocker support, or link support have only one reaction. And for hinge supports, they have two reactions. Good. Let's come to our third factor, which is the fixed support. Fixed supports. Fixed supports. So you can see how the fixed support is being represented over here. Okay. And this fixed support does not permit any movement. Good. When you come to the reactions, okay, the number of reactions for fixed support, it is 3. Okay. The number of reactions for a fixed support is 3. And that is the first one is your Rx. Second one is Ry. And the third one is a moment. Okay. And you can see that this time, your Rx is also moving to the east side, and your second reaction, which is your Ry, is moving to the north side. But for the moment, you can see that it has been represented as an anti-clockwise arc. Okay, good. The reaction consists of two force components, Rx and Ry, a couple of moments. The moment, the magnitude of Rx, Ry, and M are the 3 unknowns. Okay, this is an example of a pin supported metal. This is also a typical fixed support connection metal. You can see that for the typical fixed supported connection metal, it has been welded at this junction and has also been welded at this junction again. Okay, now you can see that the stiffness have also been placed over here to prevent movement. Okay, good. This is a typical roller supported connection concrete. Okay, so you can see that under the beam, a small ball has been placed over there, and the small ball is a roller support. And we said the roller support has one reaction, and the name for the reaction is what? Ry. Why is it Ry? Because it is moving towards the north direction. Thank you. This is also a typical fixed support connection concrete. Okay. So these are some of the equilibrium equations we are going to be using in our calculation and in our work. So let's come to the principle of superposition. The principle of superposition forms the basis for most of the theory of structure analysis. You realize that last semester we encountered principle of superposition, okay, in lecture 3. And this semester we have also encountered it again. Okay, so that should tell us that this is a very important principle which we must always keep in mind as engineers and work with it. The principle of superposition states that the total displacement or internal loading into bracket stresses at a point in a structure subjected to several external loadings can be determined by adding together the displacements or internal loadings into bracket stresses caused by each of the external loads acting separately. The principle of superposition states that the total displacement or internal loadings at a point in a structure subjected to several external loadings can be determined by adding together the displacements or internal loading caused by each of the external loading acting separately. For this statement to be valid, it is necessary that a linear relationship exists among the load, stresses, and displacements. The material must have the material must behave in a linear elastic manner so that Hooke's law is valid. The material must behave in a linear elastic manner so that Hooke's law is valid, and therefore the load will be proportional to displacement. The geometry of the structure must not undergo significant change when the load are applied. Some displacement theory applies. The geometry of the structure must not undergo significant change when the load are applied. That is, small displacement theory applies. So we are saying two requirements must be imposed for the principle of superposition to apply. Okay, if these requirements are not met, then it means that superposition, principle of superposition is not being obeyed or practiced. Okay, and the first one is the material must behave in a linear elastic manner so that Hooke's law is valid, and therefore the load will be proportional to displacement. Secondly, the geometry of the structure must not undergo significant change when the load are applied. That is, small displacement theory applies. Large displacement will significantly change the position and orientation of the load. An example would be a cantilever thin rod subjected to a force at its end, causing it to bend. Okay, so this is the formula we are going to be using in our calculations. Okay, this is these are the two formulas we are going to be using in our calculation. Please, I will urge each and every one of us to be able to put this table down on your own without looking on anything. Okay, practice make man perfect. If you're able to, okay, if it will be difficult for you, you can learn the first table for the first week. Okay, master it well. Then the second week, you take the other table. That's also a different technique. Okay, but if you can still also learn both tables, it will help you. Okay, you shouldn't just learn it, but understand it. Okay, understand it so that it will be part of you anytime, any day. Even when you sleep and they wake you up, you'll be able to put it down. Okay, good. In the table one, static determinacy of external table structure. So the column one is talking about the condition and column two is about the classification. If the relation is less than 3, then we say the structure is statically unstable externally. Also, if the reaction, which is R, is equivalent or equal to 3, then we say the structure is statically determinate externally. If the number of reactions, okay, if the number of reactions in the structure is equal to 3, the structure is statically determinate externally. And the last, but not the least, if R is greater than 3, then it also means that the structure is statically indeterminate externally. Okay. Okay. Please let's come back to basis. And this R we are seeing over here, don't get confused. These these R's, you are going to find them in your supports. Okay. The support we discussed earlier. Those supports are what your R's, or let me say your reactions are in. Okay. So we said that the roller support has one reaction. So if it is a roller support that you have seen in the question, then it means that you have to know that, first of all, you have to count the number of roller supports in there. If it is 5 roller support, then it means that you have what? 5 reactions. So in that case, if you're having 5 reactions, what is going to happen? It means that the structure is going to be what? Statically indeterminate externally. Okay. But if the beam is carrying only 3 reactions and we compare this to our standard table, you realize that if R is equal to 3, then the structure is statically determinate externally. But in a case where your roller support is just, or let me say your roller support is 1, you realize that the structure is statically unstable externally. Okay, so that is also a different phenomenon altogether. That is all about the table one. That is the table one is just a very nice experience. You could also relate it to hinges or let me say the fixed support, but we'll come back to that later. Let's go more deeper. In the table 2, in our table 2, we are going to be talking about static determinacy of internally unstable structures. Okay, you realize that the table 1 was all about static determinacy of externally stable structures. Okay, but in the table 2 is also or all about static determinacy of internally unstable structures. Good. The first column is the condition, and the second column is classification. We are saying if R is less than into bracket 3 plus EC, the structure is statically unstable externally. Okay. And your EC is your equilibrium condition. Your EC, this EC you are seeing over here, is your equilibrium condition. There is no difference between table 1 and table 2. If you maintain the second column you can maintain the second column for table 1 and table 2. Okay. It's only in the first column that you only have to apply small techniques and you are good to go. What are those techniques over here? You realize that it was only plus EC plus EC plus EC plus EC that was added. Okay, good. Also, if you come to the second aspect, they are saying if your number of reaction, which is the R is equal to 3 plus EC, and we say the EC is equilibrium condition, then the structure is statically determinate externally. In our last one, we realized that if your number of reaction R is greater than into bracket 3 plus EC, the structure becomes statically indeterminate externally. Okay, statically indeterminate externally. In fact, you can learn this table just within an hour. Okay, just within an hour, even within 30 minutes. I believe if you are able to sit down and watch this video and play it and replay it over and over and over again and read your slides along, life will be much more easier. Okay. The table is what matters to me most because your table is your key. Without a table, you realize that you are going to struggle. Okay. So you can learn table 1. When you learn table 1, the only magic you are going to apply in the examination hall is that, or in terms of you trying to remember, you are only just going to draw table 1 twice. Okay. Repeat whatever is table 1 for table 2. Okay. Then after whatever, the only changes you are going to make to table 2 is that you are going to add plus EC plus EC plus EC plus EC. And after that, you put all of them into what? Bracket, just as this. Okay. Just as this. So that is the only difference I'm seeing so far, which is the technique and also the heading. Okay. And the EC is what is causing the changes in the heading. Okay. So you could just learn table 1. Then the magic you will be applying is just come and add plus EC plus EC plus EC plus EC plus EC. Then what will you do? You are good to go. Okay. Like this, plus EC. Then you put it into brackets. Okay. Plus EC. Then you put it into brackets. You come and repeat that for the last one too. Plus EC. Okay. Also put it into bracket. You realize at the end of the day, table 1 is looking like table 2. Good. So I can clean this now so that we can know the difference between table 1 and table 2. Good. So let's talk about the degree of static determinacy. Degree of static determinacy. The degree of static determinacy is equal to the total number of reactions minus the number of static equilibrium equations. Thus, if a structure has R reaction, then the degree of external indeterminacy can be written as, that is, IE is equal to R minus 3. Okay. And this I subscript E is your degree of external indeterminacy. That's the degree of what? This you are seeing over here is your degree of external indeterminacy. Okay. And in the cases where you want to find the indeterminacy of a structure, you realize that in the tables we looked at earlier, in the third row, you were seeing indeterminacy over there, and those indeterminacy are what actually brings about the calculation of the degree of external indeterminacy. And it only happens if the number of reactions are greater than 3. So this is a formula you are going to use to calculate for your degree of external indeterminacy, where I subscript A is equal to degree of what? External indeterminacy, and your R, which is your number of what? Reaction. The number R in the equation represents the number of static equilibrium equations. The number 3 in the equation represents the number of static equilibrium equation. It represents the number of static equilibrium equation. We said the number 3 in the equation represents the number of static equilibrium equation. Let's come to degree of static indeterminacy 2. And in the degree of static indeterminacy 2, it occurs in the second table we learned initially. Okay. So in the second table, you realize that EC was playing a role, and we said EC is our what? Equilibrium. We are saying that our EC is equation of condition. Okay. Our EC is equation of condition. Equation of condition. So the degree of static indeterminacy, we are saying if internal hinges or internal hinges are introduced into the structure, the degree of indeterminacy is determined by this. Okay. Where degree of external indeterminacy, that is R is equal to number of reaction, and our EC is equation of condition. Equation of condition. So equation of condition, that is for the first one, for internal hinges, equation of condition is always equal to 1. And also for internal roller, also for internal roller, equation of condition is equal to 2. Let's come to the numerical calculations. That are the step-by-step processes you should go through to calculate or to be able to tackle any question. Okay. And these steps you are going to go through is the numerical classification steps. Your step 1, you are going to redraw the given structure. Step 2, you're going to draw the free body diagram. And in your step 3, you're going to classify the structure, whether it is determinate, indeterminate, or unstable. In step 4, if structure is indeterminate, calculate the degree of static indeterminacy. Okay, so the step 4 becomes more or less like an option. Okay, and it only applies when the number of reaction, which is R, is greater than 3. Okay, and that is what is going to make the structure become statically indeterminate externally. Okay, which is going to cause us to calculate for the degree of static indeterminacy. Good. So let's come to some work examples. And in our numerical classification of structures, in our work example, in problem 1.1, so we should classify each of the structures shown in figure 1 as externally unstable, statically determinate, or statically indeterminate. If the structure is typically indeterminate externally, then determine the degree of external indeterminacy. So these are some of our work examples. Okay, please, in a very big place, I'll urge each and every one of us to take this lecture 1 very, 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 very serious. Okay, last year lecture 1 was a major question in the paper we wrote. Okay, so a lot of people took it for joke. They didn't take it too serious, and it came. It was, for me, I see it to be the simplest among. Okay, but it was a disaster. Okay, so please, in a very big place, let's all take, especially even if you don't want to understand anything at all, please try and understand lecture 1 for me. Okay, so in the work example, the first one, you can see that a beam is being supported by a roller and a what? A hinge. Okay. Secondly, you can also see that in the second question, this is also supported by a hinge and a what? A roller. Good. Let's dive more into question 1, which is the A, before we come to what? B. In B, you realize that first of all, you will draw the diagram, okay, on your question paper. First of all, you will draw the diagram on your question paper. Then, secondly, you come and what? Draw a free body diagram. Okay. Please always try and label the parts. Okay. If you draw the free body diagram, write under it, or you can write at the right hand side, free body diagram. Okay. Then from there, where will you come to? You come to your classification. Okay. You come to the classification. So after your classification, from here, you realize that we are having two supports. We are having two supports, okay, which is supporting the beam. But you have seen that, or we have learned earlier that Roller supports have one reaction, okay, which is moving towards the north side, and hinge support have two reactions, whereby one is moving to the north side and one is moving to the east side. Good. Where your first one is your hot, Rx, okay, and your second one becomes your hot, Ry, okay. For the roller support, this is also Ry. You said the roller support has only one reaction, and their reactions are moving towards the north side. Okay, in your classification, so if hinge support is having two reactions and roller support is having one reaction, if you add them, realize that you are going to get three. So we said number of reaction, comma, is equal to what? Three. Now that we know that the number of reaction is equal to three, we have to classify the structure. Okay, we have to classify the structure. In doing so, we have to know the number of reactions, which we have already done. If we already know the number of reactions, we can compare from our table, the table we learned earlier, okay? And in the table we learned earlier, what did we say? We said that in this case, you realize that this A we are looking at, it does not have any what EC in it. It does not have any equation of condition in it. Okay. So because of that, we can consider table one. Okay. And in the table one, what do we say? We say that if the number of reaction is what? Equal to what? 3, then the structure is statically determinate externally. Okay. So that is how we are going to classify it. That is how we are going to classify A, the A part of the question, or let me say the first structure. Okay. So the first structure, you realize that it has three reactions. Okay. And the three reactions, if it has three reactions, then how are we going to classify it? We're going to say that, okay, R is equal to 3, and therefore if R is equal to 3, the structure becomes what? Statically determinate what? Externally. Statically determinate externally. Okay. Statically determinate externally. You say R is equal to 3, which is equivalent to what? Statically determinate. Good. So we are done with question one. That is all. That is all you must know. Okay. That is all you must know. As I told you earlier, my best advice I will give you is that try as much as possible not to forget your number of supports. Okay, the three basic type of supports we looked at, which we said the ruler, the fixed, and the hot hinge. Okay. For the ruler, we have different types. You may either meet a ruler, a rocker, or a link support in the question. But you should always know that those kinds of support has only one reaction. That is your key. But if you also identify that it is a what? A hinge support, then you also have to remember that it has two reactions. Okay. In cases where you encounter fixed support, then you have to also remember that it has three reactions, where we said it has the first reaction moving towards the east side, the second reaction moving towards the north side, and the third reaction becomes a moment. In some cases, it may be an anti-clockwise movement. In some cases, it may be a clockwise movement. The nature of the question would determine that. Thank you. So in our question, in our second question, or let me say the B part of the question, You can see that this beam over here or this structure over here is being what? Supported by a, a roller and a hinge in this case. Okay. But in this case, you have to open your eye. Oh. You have to open your eye. Pa. You realize that structure, or let me say, question A and question B. Question A and question B, they are all having the same number of structures. They look alike. But you can see that over here, they've not written anywhere over here hinge. You have to take time and study the question and understand the question well before you even start to answer the question. But if you come and study the second question, you realize that they have written hinge on top of the structure. Then you have to know that no, this hinge they have written over here is an what? Equation of condition. And that equation of condition is your what? Is your EC. That equation of condition is your EC. Okay, so how many equation of condition do we have over here? This equation of condition we have over here becomes our what? Hinge that you are seeing over here, and it's just one. Okay, this hinge you are seeing over here is different from the one I have circled. The one I have circled is a support, but this one over here is a problem. And what is the problem? The problem is equation of condition. Okay, good. So first of all, as we discussed, you always have to draw the original structure on your question paper, okay, to tell the examiner that, oh, this is the structure I am classifying. So when you draw your structure, you write on your right-hand side of it, original structure, label it, okay? And you come and draw a free body diagram. The free body diagram is just one line of this. You just draw a straight line, then you come and put your reaction. We say the roller support has one reaction. So you put it over there, one reaction. And the reaction is known as what? R what? Y. R1. And the second one is a hinge support. And the hinge support is having two reactions. The first one is what? Rx. And the second one is what? Ry. Okay. Also, because it's having a hinge, or let me say equation of condition inside of it, you have to represent that in your free body diagram. Okay, you have to represent that as this. Okay, and label the part fair. Okay, you can see that it's just a small circle that has been placed in the line. Okay, so in our classification, the number of uh, reaction is equal to 3. In our classification, the number of reaction is equal to 3. The number of reaction is equal to 3. And equation of condition becomes 1. The equation of condition becomes 1 because we can only see one in it. Okay, the whole of this structure, there is only one of this in it. So that is why I've written equation of condition, which is the EC is equal to 1. Bear in mind, this is a very big please. You always have to remember and add that as part of your classification. If you fail to do so, you'll be penalized. It will cause you to lose mark. Okay. So if you're able to draw the free body diagram, just be able to know the kind of support and remember the number of reactions they are having. Add them and you write number of reaction R is equal to 3, equation of condition, comma, EC is equal to what? 1. Good. From there, because there is an equation of condition in the structure, we have to apply uh, the knowledge of the second table. Okay. And that is, we are saying 3 plus EC is equal to what? 3 plus 1 is equal to 4. And this EC you are seeing over here is just this one we have written over here. Okay. And it's the same as this you are seeing over here. You can see that this is only one. Okay. This is only one. And that is what is causing this to become 4. Okay. So at the end of the day, 3 plus the EC, which is the 1, is equal to 4. Now, we can either classify it whether it is what? Statically determinate, statically indeterminate, or unstable. So, from what we have learned so far, what do you think this structure, or how do you think it's going to be classified? Once you have seen this EC in the structure, then you have to know that table 1, you have to forget about table 1 and use table 2. Okay. So in this case, we're using table 2. So from the idea of table 2, you realize that from the idea of table 2, you realize that they are saying if R is less than 3 plus, if R is less than 3 plus EC, then the structure is statically unstable externally. Okay. So from page 39, you realize that in our problem over here, because R, or let me say R is less than, because R is less than 3 plus EC, you realize that this structure became what? Statically unstable externally. Okay. It made this structure become statically unstable externally. Okay. So it made the structure became statically unstable externally. And it became statically unstable it became statically unstable externally because R was less than 3 plus EC. And we say that EC is the what? Equation of condition. Let's look at this last example and go and solve some of the trial questions on our own. So in this problem, you realize that this is our original problem. As we discussed earlier, you always have to draw the original problem on your question paper. For a mark, if you don't draw it, you lose mark. If you draw it, you label the part original structure. You label the part original structure. Okay. Then from there, you come and draw a free body diagram. Okay. From there, you come and draw a free body diagram. And then after drawing the free body diagram, or even before you draw the free body diagram, you have to take note. How many supports do I have in there? Okay, let me count my number of support. I have 1, 2, 3. Oh, okay, I have 3 supports. Okay, it means that these supports over there are having some number of reactions in there. But before I know the number of reactions, I have to know the kind of support it is, because every support has its own reaction it possesses. Okay, this one is a roller support and it's having only one reaction. You say that reaction is the what? RY. That reaction is the RY. Okay, the second one is also a roller support, and that reaction is also an RY. The third one in this case is a fixed support. Because it's a fixed support, you realize that because it is a fixed support, you realize it is having 3 reactions. Okay, the first one, which is a what? Rx moving towards the east side, and the second one is All right, moving towards the north side. The third one is a moment. Okay, the third one is a moment. Bear in mind, the moment may be clockwise or anti-clockwise depending on the nature of the question. Okay, so if when we come to our classification, one, therefore, how many reactions are we having over here? Let's count. Yeah, one, two, three, four, five. Okay, we realize that we're having five reactions, so we can write over here number of reactions is equal to 5. Secondly, R is greater than 3. So, secondly, we are saying if R is what? Greater than 3, then the structure becomes statically indeterminate. Yes, of course. This is an indeterminate structure because you realize that we say that if before the thing to be determinate, it has to be what? Equal to 3. But in this case, it is more than the 3. So it becomes what? Indeterminate. Okay. Once you realize R becomes 5 you realize it becomes indeterminate. In this case, you're going to be using table 1. And why are we going to be using table 1? We're going to be using table 1 because we don't have any what? EC or equation of condition in this problem or structure. Good. So after being able to classify it as statically indeterminate, the next thing you do is come and calculate for the degree of static indeterminacy. Degree of static indeterminacy. Degree of static indeterminacy. Degree of static indeterminacy. Okay, and our degree of static indeterminacy is equal to what? R minus 3. What we learned earlier. Our degree of static indeterminacy. We say anytime you realize the number of reaction is more than 3, you have to remember you will be calculating for degree of static indeterminacy. Okay, that is a note you have to put somewhere. Okay, jot down somewhere. Anytime the anytime the number of reaction is more than 3, the support, or let me say the structure, is going to become what? Statically indeterminate externally, and because of that, we are always going to find the degree of static indeterminacy. The formula for finding for the degree of static indeterminacy in a case whereby there is no equation of condition in the problem, then it means that we are going to apply the lesson learned from table 1. Okay, so you realize that in this case, our degree of static indeterminacy is going to be equal to R minus 3. Okay, our R over here is our 5. So the 5 minus the 3 becomes what? 2. 5 minus 3 is equal to 2. At the end of the day, statically indeterminate, or let me say at the end of the day, the structure becomes statically indeterminate to the second degree. Okay, because after calculating for the degree of static indeterminacy, we had what? 2. So you say that therefore the structure becomes statically indeterminate to the second degree. Back when I was in uh, level 100 second year, some of my colleagues and I, we even have to name each other after this. Okay. And with time, we got familiar with some of the words. Okay. Most of us use it as slogans. When you see your friend, you say statically indeterminate. Okay, with time you get used to the concept. Okay, that alone is a big motivation. Okay, yes, saying small, you realize that life will become much more easier. I know that this semester the workload is very much tight, but you only just have to try and develop strategies. Develop strategies. Okay. So the structure becomes statically indeterminate to the second degree. So in our solution D, you realize that this problem over here, or let me say in our original structure, first of all, we say you have to what? Redraw the structure. Okay. Redraw the structure on your question paper. After redrawing the structure on your question paper, what will you do next? After redrawing the structure on your question paper, what will you do next? You have to label the part. Okay. And label the part and write on it original structure. Original structure. Then from there, you come and draw a free body diagram. Before you draw the free body diagram, you have to check whether there is an EC in there or not. You say the EC is the equation of condition. Okay, let's count. We have one EC over here. The EC will always be labeled for you. And we also have a different EC over here. So your first one, this is EC. So you realize that this one become 1, and this one also becomes what? 2. So at the end of the day, how many EC are we having? We have 2 ECs. Okay, so in drawing your free body diagram, you have to remember to represent the 2 EC you have seen also in the free body diagram. Okay, to make your free body diagram more valid. Okay. Over here, we have a roller support, and we say a roller support has one reaction. So this is our reaction Y. This is also our reaction Y. Okay. For this is also a roller, so this is also a roller support. The third one is a what? It's a fixed support. And the fixed support, it has 3 reactions. Okay. So Rx, reaction X, reaction Y, and the moment. From there, we only come to our classification. In our classification, our number of reaction R is equal to 5. In our classification, realize that our number of reaction R becomes 5. If you count, you are going to realize that we have 3 supports over here. And the 3 supports entails 1 fixed support and 2 rollers. You said the rollers possess only 1 reaction. So if we have 2 rollers over there, then it means we have what? 2 reactions. If fixed support have 3 reactions, if we add the 2 to the 3, we are going to get 5. So at the end of the day, realize that the number of reaction over here is 5. And the equation of condition, as I told you earlier, this is 1, this is 2. So our EC becomes 2. Because there is an EC over here, we have to calculate for uh, we have to calculate for this. Okay. So at the end of the day, we're going to add 3 plus what? EC. Okay, we're going to add the 3, and we say that this 3 over here is a what? This 3 over here, we are saying is a constant. Okay. So 3 um so 3 plus EC is equal to what? 3 plus 2. This is going to give us 5 at the end of the day. It's going to give us 5 at the end of the day. So at the end of the day, you realize that